Hello students. Today we will talk about electrostatic potential energy of dipole. We will derive expression for the potential energy of dipole, and we will also see how potential energy varies if we change orientation of dipole in electric field. So let us start. To understand today's topic, we need to recall some of the previous topics. First of all, we should be knowing that absolute potential of any charge q at given point A can be found out by the following expression. V of A is equal to negative integration of electric field over displacement from infinity to point A. And we also know that potential energy U can be expressed in terms of potential with the expression U is equal to QV or delta U is equal to Q delta V. Actually, in delta U is equal to Q delta V, if we make assumption that initial potential energy and initial potential are zero, then we get U is equal to QV. Apart from this too, we should also be knowing that whenever we move any charge q in electric field by distance d, the potential energy of the charge can be given as U is equal to minus QED cos theta. What is theta here? Angle between QE and D. So with this prerequisites clear, I think we can start with today's topic. So let us start. Consider uniform electric field as shown here with positive charge on left side, negative charge on right side, and let us place a dipole in this field in such a way that dipole moment is upward. So what is the angle between dipole moment and electric field? As we can see here, angle between dipole moment and electric field is 90 degree. And what we can say about the comfort level of dipole? Obviously, dipole is not 100% comfortable. It will try to change its situation by giving itself rotation by 90 degree and 90 degree clockwise. So we can say that if dipole is trying to change its situation, this is definitely not minimum potential energy configuration, and may not be maximum, but definitely not minimum potential energy. So once we have expression for the potential energy of dipole, we'll verify that potential energy when angle is 90 is maximum or minimum or some intermediate value. Let us consider uniform electric field as shown here with positive charge on left side, negative charge on the right side, and let us place a dipole in such a way that the dipole moment of the dipole is upward and downward, and electric field is going right side. So what is the angle between the two? Angle between the two is minus 90 degree, or else you can say it is 270 degree. And what is the situation of dipole right now? As discussed earlier, as we saw earlier, this dipole is also not comfortable, and hence it will rotate. And in which direction it will rotate? It will rotate in anti-clockwise manner. But after 90 degree, it will also settle down. So we can say that here also potential energy of dipole is not minimum, and it is trying to reach minimum potential energy configuration. So we'll verify this once we have expression for potential energy of dipole. Now there is one more way we can place dipole in this electric field. We can place it in such a way that dipole moment and electric field both are parallel. So as shown here, P is going from left to right and electric field is also left to right. So what is the angle between the two? Angle between P and A is 0. And in this situation, when angle is 0, what we can say about the potential energy of dipole? Potential energy is actually reflecting comfort level. Is the dipole comfortable here? So looking at the situation, we realize that dipole is very much comfortable because positive charge of dipole is facing negative side outside, and positive charge of external field is close to negative charge of dipole. So potential energy of dipole must be minimum. So once we have expression, once we derive the equation for potential energy, we should be getting this result that when theta is 0, potential energy of dipole should be minimum. We'll explore one more possibility where we have uniform electric field, again the same, and we'll place dipole now in such a way that the dipole moment is opposite to the external electric field. and obviously here the positive are facing, negative are facing, and so we can understand that dipole is not at all comfortable in this situation. So if it is not comfortable, what we can say about its potential energy? Obviously potential energy of dipole when angle between P and E is 180 must be maximum, because more the uncomfort level, more the potential energy. So when theta is pi radian or 180 degree, potential energy of dipole should be maximum. So we'll verify this also, that once we have expression, if theta is 180, if theta is considered 180, is the potential energy maximum? We'll check once we have expression for potential energy. Now, before we get into the derivation part of the expression, let us understand that how potential varies when we move from one point to another point in uniform electric field. So here we have uniform electric field, and to understand the work done to move any charge in this field, here charges are shown. Left side is positive, right side is negative. So we have field lines going from left to right. And in this field, we consider 3 points A, B, and C as shown here, and we'll see how much is the potential at A point or C point or B point, or what happens to the potential when we go from A to B or A to C or C to B. So if I want to find out potential at point C, what I should be doing? We know that potential is nothing but work done to bring a unit positive charge from infinity to given point C. So if I want potential at point C, I should bring unit positive charge from infinity to point C, and if the work done is Vc, I would say Vc is the potential at point C, isn't it? And what if I want potential at A point? If I want potential at A point, I should come with my unit positive charge from infinity to point A, and if I notice that work done is VA, I would say VA is the potential at point A. Now, what should be the relation between VA and VC? VA should be more or VC should be more, or both are equal. So as we can see here, A point is very close to positive charge, and C point is comparatively at larger distance. So where we need to spend more energy? To reach point A or to reach C point? Now obviously when we come to A point, we are coming close to positive charge, so we'll be facing more repulsion, and hence we'll need to spend more energy. And so we can say that potential at A point should be more than potential at C. But what if I compare potential at B and C? Now we know that when we come from infinity to point B, we are coming at same distance as that of C, and hence if potential at point B is VB, what should be the relation between VC and VB? Now as C and B are at same distance from positive charge, at same distance from negative charge, work done to reach point B or work done to reach point C should be equal, and hence we can say that VC is equal to VB. So when we go from A to C, potential decreases. When we go from C to B, potential increases. But if we go from C to B, when we go from A to C, potential decreases, C to A, potential increases. But if we go from C to B or B to C, potential is not changing, hence work done is 0. Okay, so C and B are equipotential points, we may say. So let us start with the derivation. We consider the same electric field which is in x direction, so E is equal to EI cap we may consider, and we place dipole in such a way that at A point we have negative charge, at B point we have positive charge. So what is the direction of dipole moment here? Direction of dipole moment is from negative charge to positive charge. So this is how we have P direction, and if the separation is 2A, we can say that angle between P and A is theta. So for this situation, we'll derive expression for potential energy of dipole. Now here, for convenience, we consider one more point C, in such a way that BC is perpendicular to the field and AC is along the field. So as we go from A to C, if the distance is delta x, we know that potential changes. If you go from A to C, potential decreases. But if we go from C to B or B to C, delta VBC is 0. Potential difference between B and C is 0, hence delta VBC is 0. But potential difference between A and C is not 0. So as we go from A to C or C to A, we will have some change in potential. And if we have delta V, we can multiply it with charge. And if we multiply it with charge, if we multiply V with Q, what we'll get? We get potential energy. So that is the idea. With that logic, we will derive expression for potential energy. So let us get into maths part. So this is the situation, and we know that dipole moment here is P is equal to Q into 2A, and from definition of potential, we know that potential is given as negative integration of electric field over displacement. But if the displacement is less, we don't need to integrate, and in that case, what we can do, we can write this equation as dV is equal to negative E dot dr, isn't it? When displacement is less, electric field may be considered constant. Or else you can also write it as delta V is equal to E with negative sign E delta R. And in our case, in our particular situation, we know that if I consider AC, it is in x direction, and electric field also is in x direction. So what is the angle between AC and electric field? It is 0. So for this particular situation, I can write delta V as minus E delta x, because we know that as we go from B to C, potential is not changing. So in this case, change in potential can be expressed as minus E delta x. So now, uh, as I know that delta V is equal to minus E into AC, uh, look at the figure and apply cos theta formula to triangle ABC. What is cos theta? So we know that cos theta is adjacent by hypotenuse. What is adjacent side? Adjacent side is AC, or you may write it as delta x. Okay, and hypotenuse is AB or else 2A. So what is the value of AC? AC is equal to 2A cos theta. So in our equation of delta V, if I replace AC with 2A cos theta, I get delta V to be minus E into 2A into cos theta. Once we have potential difference, we can multiply both sides with Q, and if we multiply delta V with Q, what do we get? Potential energy. So now we can try finding out potential energy. So I know that delta U is equal to Q delta V, and delta V is minus E into 2A into cos theta. So delta U is equal to Q into E into 2A into cos theta. But what is Q into 2A? Q into 2A is dipole moment P, and hence I can write delta U as minus PE cos theta. But we know that AB cos theta is A dot B vector A dot vector B, so PE cos theta can be written as minus P dot E, isn't it? And but this is delta U. How do we get U from delta U? If we make assumption that initial potential energy is 0, then I can rewrite this equation as U is equal to minus P dot E. And so this equation can be written as U is equal to minus P dot E. And now we will verify our previous predictions with this equation. We had 4 situations considered, and for 4 situations we had some predictions. So now with the equation available, we can verify whether we were right about our prediction about potential energy or not. So let us try. First, we did assume that when dipole moment and electric field are at 90 degree as shown here, the dipole is not comfortable and so it will try to rotate itself by 90 degree in clockwise fashion and then it will settle down. So potential energy in this case was not expected to be minimum. So let us see with expression what we get. So with expression now I have P cos theta which is P cos 90 and hence potential energy is 0. Now 0 potential energy is not indicating that it is minimum. We can have negative value also. And in second case also where we have dipole moment downward and electric field in the same manner, the angle was 270 and we did predict that dipole again here should have same potential energy because here also dipole will try to give itself rotation by 90 degree but in opposite direction. So potential energy in first and second situation should be same. Let us see what equation tells us. So in equation, if I substitute theta value, angle between P and E is 270 here or minus 90 you may say. What is U value now? 0. So when P and E are at 90 plus or minus 90 degree, potential energy of the dipole is 0. What if the dipole moment and electric field are parallel? We felt that potential energy in this case should be minimum because the negative, positive, positive, negative are facing each other of external charge and the charges of dipole. So this is the most comfortable situation for the dipole and we expected that potential energy here should be minimum. What is the angle between P and E here? Both are in the same direction, so angle is 0. So PE cos theta becomes PE cos 0 and then with negative sign we have minus PE. So U is equal to minus PE is the minimum potential energy of dipole. And if we consider dipole moment and electric field to be in opposite direction, what is the angle now? 180 degree. And then what formula tells us? Cos 180 is minus 1. So potential energy is plus PE. So maximum potential energy of the dipole is plus P, minimum potential energy of the dipole is minus PE. So what if you take dipole from maximum potential energy situation to minimum potential energy situation? So what I'm talking about is flipping the dipole by 180. If we flip it by 180 degree, we go from plus PE energy to minus PE energy and hence work done is 2 PE. And that is applicable for all other situations. Just look at initial potential energy, final potential energy. Difference of the two is work done. Okay, so that is how we can find out work done to rotate dipole in given situation. So let us conclude now. So now we know that electric potential energy of dipole can be given as U is equal to minus P dot E or PE cos theta, where theta is angle between dipole moment P and electric field E. And we also know that when angle between P and E is 0, the potential energy of dipole is minimum, which is minus PE. You cannot have potential energy of dipole less than minus PE. And if we consider P and E to be in opposite direction, angle becomes 180 and at that time U becomes plus PE, which is the maximum possible value of potential energy for any dipole placed in electric field. For angle values minus 90 or plus 90 degree, the potential energy of dipole is 0. So that was the topic and these are the special cases. I hope you could understand. Thank you.